Turbines are the heart of a power plant. Without them, plants couldn't generate the electricity that's used by millions of people. As an operator, an important part of your responsibility is to keep the turbines in your plant running smoothly and safely. The operation of a turbine involves several valves and several support systems. Therefore, you need to know how these valves and support systems work. In this unit, we'll see how they work, and we'll take a close look at why they're important. It takes a lot of valves to operate a turbine. As you may know, the purpose of any valve is to control the flow of a substance. They control flow in one of two ways: by turning it completely on or off, or by regulating its rate. In the case of a turbine, valves control the flow of steam. Steam drives the turbine, but to drive it, the steam has to follow a certain path. It's the turbine valves that control the flow through this path. To get a better idea of the functions of the turbine valves, let's look at a simplified diagram of the steam's flow path through a typical turbine. Steam from the superheater section of the boiler travels to the high pressure, or HP turbine. From the HP turbine, steam flows through the reheater for additional heating. The reheated steam goes to the intermediate pressure, or IP turbine, then to the low pressure, or LP turbine. From there, the steam is exhausted to the condenser, where it's condensed back into water. Finally, the cycle is complete when the condensed steam is routed back to the boiler. To control this steam flow, turbines generally use 4 sets of valves: the main stop valves, the control valves, the reheat stop valves, and the intercept valves. The function of these valves varies depending on how the turbine is operating. For example, during normal operation, the main stop valves admit steam to the HP turbine. During emergencies or shutdowns, the main stop valves shut off the flow of steam. And during startup, the main stop valves can regulate the rate of steam flow to the HP turbine. The control valves regulate the rate of steam flow to the HP turbine during normal operation. However, during emergencies or shutdowns, they serve as a backup to the main stop valves to shut off the flow of steam into the HP turbine. The reheat stop valves admit reheated steam to the IP turbine during normal operation and shut off the flow of steam during emergencies or shutdowns. Finally, the intercept valves admit reheated steam to the IP turbine during normal operation, but during emergencies or shutdowns, they can regulate or shut off the flow of steam to the IP turbine. As we said, the main stop valves admit steam to the HP turbine during normal operation, but shut it off during shutdowns or emergencies. Shutting off the flow of steam is called a turbine trip. The term turbine trip can apply to any situation when the valves of the turbine are closed and the turbine is out of service. But during the course of this unit, we'll use it to refer only to shutdowns that are unplanned and occur under emergency conditions. To understand how main stop valves work during trips or during normal operation, let's look at a simplified cross-section of one. Keep in mind, though, that the main stop valve you'll see here and the other valves you'll see later may not be exactly like the ones in your plant, but they are similar enough to help you understand your own plant's turbine. Here we see a typical main stop valve with steam lines leading into and out of the valve. Steam from the boiler enters the valve through this line and leaves the valve through this line, which is connected to the control valves. The main stop valve consists of a valve disc, a valve seat, a valve stem, and a hydraulic actuator. The hydraulic actuator has a piston that's acted upon by hydraulic oil and a compression spring. During normal operation, the valve is held fully open. It's opened and held open by hydraulic oil pressure on the piston. The piston compresses the spring and pushes the valve stem. The stem lifts the valve disc off its seat. In this position, steam flows toward the high-pressure turbine. When the turbine is tripped, the hydraulic oil is quickly bled from underneath the piston. As this happens, the spring expands, forcing the valve disc back on its seat. Steam pressure also helps to close the valve by pushing the valve disc towards the seat. This shuts off the flow of steam toward the HP turbine. Now you've seen how a main stop valve works to admit or shut off the flow of steam to the HP turbine during normal operation and during trips. Remember, though, that some main stop valves can also regulate the rate of steam flow during startup operation. Generally, there are 2 to 4 main stop valves on a turbine, and at least one performs the function of regulating flow during startup. The main stop valve that regulates flow is a little different from the valve we just looked at. So let's see how this valve is constructed, and then we'll see how it works. The valve in this illustration is similar to the one we saw earlier, except it has an internal bypass valve. The internal bypass valve consists of a valve disc and a valve seat. Also, holes are drilled in the main stop valve disc. As the valve stem is moved toward the open position, the bypass valve is lifted off its seat. This allows a small amount of steam to flow through the holes in the main stop valve disc. This arrangement provides a fine control of steam flow, enabling the speed of the turbine to be increased gradually during startup. When the turbine is up to speed, the bypass valve disc is raised more, lifting the main stop valve disc off its seat. In addition, the other main stop valves are also open. In this position, there is a full flow of steam towards the turbine. When the main stop valves are fully open, the flow of steam into the turbine is regulated by the control valves. The turbine control valves have the job of controlling either the turbine's speed or the turbine's power output. To see how they do this, let's take a look at another illustration. There are usually from 4 to 8 control valves that work together to provide a fine control of steam flow. Steam is routed from the main stop valves to the control valves through this steam line, and it's sent to the sections of the turbine's nozzle block through these lines. Each valve feeds only one section of the nozzle block. The control valves are operated by hydraulic actuators. These valves regulate steam flow to the turbine by opening and closing in sequence. As each valve opens, more steam is admitted to the turbine. At normal turbine operation, the control valves are positioned as necessary to compensate for changes in load. At full load, all the control valves are almost completely open, allowing a full flow of steam to the HP turbine. Now that we've seen how main stop valves and control valves work separately, we need to learn how they work together. This is important because during startup, the operation of one set of valves is related to the operation of the other. In this illustration, we've combined a main stop valve and a set of control valves. Although there are usually 2 to 4 main stop valves, we've only shown one here for simplicity. We've also included 2 steam pressure gauges. This gauge indicates the pressure from the boiler to the main stop valve. And this gauge indicates the pressure from the main stop valve to the control valves. During startup, all of the control valves are usually wide open, and steam flow is controlled by the main stop valve's internal bypass valve. This arrangement allows a small amount of steam to be admitted to all sections of the nozzle block, which causes the turbine to rotate. This condition is called full arc admission. Full arc admission allows the turbine to be heated evenly because steam is distributed equally to each section of the nozzle block. The turbine is kept in full arc admission until the internal bypass valve is almost fully opened. With the main stop valve disc on its seat, there is a greater pressure on the top of the valve disc than on the bottom, creating a large differential pressure. Most main stop valves cannot open unless the pressure under the valve is at least 80 to 85% of the pressure on top of the valve. To open the main stop valve, the pressure differential must be decreased. This is accomplished by shifting control of the turbine from the stop valves to the control valves. The point at which control is shifted is called the transfer point. At the transfer point, the control valves are gradually closed down. As the control valves close, the pressure exerted on the bottom of the stop valve disc increases. Eventually, the pressure under the valve will be at least 80 to 85% of the pressure on top of the valve. When this happens, the main stop valve can be opened. When the main stop valve is fully open, the control valves are controlling the flow of steam to the turbine. As load demand changes, the control valves open and close as necessary. What we've just gone through gives you a pretty good idea of how main stop valves and control valves work during startup and transfer of turbine control. In the next part of this program, we'll look at other valves that play important roles in the operation of a steam turbine. Before we return, though, you should review what we've covered on main stop valves and control valves by reading the material in your text and answering the questions. If you need any help, just ask your instructor. In the last segment, we followed the flow of steam from the boiler through the main stop valves, through the control valves, and into the HP turbine. In this segment, we'll take a look at the valves that control the steam flow through the rest of the turbine. The valves that do this are the reheat stop valves and the intercept valves. To see how these valves function, let's look at the flow of steam as it leaves the HP turbine. Steam from the HP turbine passes through the cold reheat line and into the reheater. At the reheater, the steam gets additional heating so it can perform more useful work in the rest of the turbine. The reheated steam then travels through the hot reheat line, through the reheat stop valves, through the intercept valves, and into the IP turbine. Reheat stop valves and intercept valves are generally constructed like main stop valves, except neither has an internal bypass valve. The way they work is also similar. Both the reheat stop valves and intercept valves are operated by hydraulic actuators. During the normal operation, the reheat stop valves are fully open, so reheated steam is admitted to the IP turbine. During trips, these valves are closed, and the reheated steam is shut off from the IP turbine. The intercept valves are also open during normal operation and closed during trips. There is one condition, however, when the intercept valves are positioned to regulate the flow of steam into the IP turbine. This condition is called a load rejection. A load rejection is a sudden reduction of electrical usage in the power system. With no electrical load, the turbine may overspeed. A better way to understand this is through an analogy. Suppose you were driving your car at 55 miles an hour and you put the gear shift in neutral without letting up on the gas. What would happen? As you know, the engine's RPM would increase enough to possibly damage the engine. During a load rejection, a turbine reacts pretty much the same way. Fortunately, though, turbines are equipped with a system to prevent overspeeding in the event of a load rejection. If we go back to our illustration, we can get a general idea how this works. Basically, what happens during a load rejection is that the control valves close. Although this would effectively stop the flow of steam to the high-pressure turbine, there would still be a significant amount of steam remaining in the reheater. If this steam were allowed to travel through the intermediate and low-pressure sections of the turbine, it could cause the turbine to overspeed, and this is where the intercept valves enter the picture. This simplified illustration shows a cross-section of an intercept valve and the steam lines leading into and out of it. This line connects the intercept valve to the reheater, and this line connects the intercept valve to the IP turbine. We're also including a gauge that measures turbine speed in RPM. Right now, the turbine is at normal operating speed, and the valve is fully open. However, when the turbine speed reaches about 101%, the intercept valves begin to close. When the turbine speed reaches about 105%, the intercept valves are completely closed and steam flow through the turbine is stopped. Therefore, the turbine starts to slow down. Even though the intercept valves have shut off the flow of steam to the IP turbine, there still may be steam trapped in the reheater. However, once the turbine slows down to a safe speed, the intercept valves could gradually reopen and let the trapped steam out of the reheater. Since intercept valves are regulating valves, the flow of trapped steam can be adjusted to control the turbine speed. Well, we've seen the basic operation of reheat stop valves and intercept valves. Now let's follow the flow of steam as it leaves the intercept valves and travels through the remaining sections of the turbine. The steam leaves the intercept valves and travels through the intermediate section of the turbine. Then the steam is directed to the low-pressure turbine through a crossover pipe. As you can see, there are no valves between the intermediate and low-pressure sections. The steam then flows through the low-pressure turbine stages and is exhausted to the condenser. Up to this point, we've discussed the flow of steam through the turbine, and we've talked about the valves controlling that flow. Now is a good time to review this information in your text and answer the questions at the end of the section. When we come back, we'll take a look at other valves associated with turbine operation. Be sure to ask your instructor to answer any questions you have about turbine flow path and valves. So far, we've discussed valves that are responsible for actually controlling the flow of steam through a turbine. But there are valves on turbines that perform other important functions as well. These valves are sometimes called auxiliary valves. We'll take a look at some of these auxiliary valves and discuss them separately in terms of their purpose and operation. Not all turbines are designed the same, so the turbine in your plant may not have some of the valves we'll look at in this part of the program, but you'll find them on most turbines being used today. The three types of valves we'll discuss are ventilator valves, emergency blowdown valves, and startup drain valves. The ventilator valve is the first type we'll look at. An important function of the ventilator valve is to prevent the turbine from overheating in the event of a turbine trip or shutdown. To understand how this valve works, let's first see how a turbine could overheat if it's tripped or shut down. If the turbine trips, the valves that control the flow of steam through the turbine close. When these valves close, steam is bottled up in the high-pressure turbine. However, during this condition, the high-pressure turbine blades are still rotating. Since the steam in the HP turbine has no place to go, the rotation of the blades through the trapped high-pressure steam could generate a tremendous heat buildup and possibly damage the turbine's internal parts. Now let's see how the ventilator valve prevents this. The ventilator valve is connected to a steam line between one of the control valves and the HP turbine. The ventilator valve discharges directly to a low-pressure area, normally the condenser. When the turbine trips, the ventilator valve opens. When it opens, a small amount of steam is drawn from the reheater through the rotating turbine blades through the ventilator valve itself, and then the steam is exhausted to the condenser. This flow of steam prevents heat from building up in the HP turbine. Overheating is not the only problem caused by a turbine trip or shutdown. Another possible problem is overspeeding. We've already seen that during a load rejection, intercept valves prevent overspeeding. But during a turbine trip or shutdown, a different valve prevents overspeeding. This valve is called the emergency blowdown valve. To understand how the emergency blowdown valve functions, we need to look at a turbine in a little more detail and examine a condition that may cause overspeeding. Here we have a simplified cross-section of a turbine. We still have the HP, IP, and LP turbines, but we've also included the turbine rotor and blades and seals between the different turbine sections. The seal between the HP and IP turbine is sometimes called the mid-span seal. During normal operation, the mid-span seal keeps steam from these two sections of the turbine from leaking into each other. As we saw before, when the turbine is tripped, a large volume of high-energy steam is trapped in the high-pressure turbine and reheated. The pressure of the steam in this section is about 400 to 500 pounds per square inch. But the pressure of the intermediate and low-pressure turbine is below atmospheric pressure because the condenser remains in operation, creating a low pressure. Because of that low pressure, steam tends to be drawn through the mid-span seal. Steam leaking through the mid-span seal expands through the intermediate and high-pressure sections of the turbine. If enough steam leaks through, it could continue to drive the turbine, possibly causing it to overspeed. Leakage through the mid-span seal is minimized by the emergency blowdown valve. The emergency blowdown valve connects the mid-span seal to the condenser. This valve is closed during normal operation. However, when the turbine trips, it opens, and steam is routed directly to the condenser. Since steam leaking through the mid-span seal is routed away from the IP and LP turbines, the possibility of overspeed is reduced. We've now looked at auxiliary valves designed to handle overheating and overspeeding caused by turbine trips and shutdowns. In addition to overheating and overspeeding, another problem the turbines encounter is moisture in the steam lines. This moisture must be removed before steam is admitted to the turbine. Once turbine startup has begun, any moisture left in the steam lines can cause severe damage to the turbine. The removal of moisture is critical because water droplets can have a bullet-like effect if they strike a fast-moving turbine blade. The droplets can actually chip off small chunks of the blade. However, turbines are equipped with valves that get rid of these droplets before they can strike the blades. These are called startup drain valves. In this block diagram, the startup drain valves are located at points in the steam path where moisture is likely to collect. Generally, the moisture that's collected is routed to the condenser. These drain valves are opened before starting the turbine and are usually not closed until the turbine is carrying load, when enough time has elapsed so that there's no moisture left in the steam or turbine pipes. Startup drain valves are operated either manually or by motor. Some drain valves are operated locally at the drain, and some are operated remotely from a centralized valve pedestal. These hand wheels are connected by linkage to the startup drain valves. If startup drain valves are motor operated, they can be controlled by the operator or by an automatic control system. Well, you've seen how many of the important turbine valves work, and you've seen how these valves control the flow of steam through a turbine. This is a good time to stop the tape and increase your understanding of what we've covered so far. You can do this by reading over the material in the text and answering the questions. For a turbine to operate efficiently, steam must be prevented from leaking out of the turbine, and air must be prevented from leaking in. Steam leaks are extremely dangerous. Superheated steam inside the turbine may have a temperature as high as 1,000 degrees Fahrenheit. If this high temperature steam leaks out of the turbine, it could seriously burn anyone who's exposed to it. In addition, steam leaking from a turbine causes heat to be lost and money to be wasted. It's like leaving your front door open in the wintertime. Air that gets inside a turbine also reduces a turbine's efficiency. For example, some sections of a turbine operate under a vacuum. If air gets inside these sections, the vacuum will be reduced. As you probably know, when vacuum is reduced, the turbine becomes less efficient. Also, air leaking into a turbine can cause a condition called thermal stress. Thermal stress is caused by two substances of different temperatures coming into contact with each other. In the case of a turbine operating under load, the surrounding air is considerably colder than the surfaces inside. If air leaks in and hits the hot turbine metal, it could cause turbine parts to expand and contract unevenly and eventually crack. Now that we know some of the problems that air and steam leaks can cause, we need to see how leaks are prevented. In short, this is accomplished by sealing the areas of a turbine where leaks may occur, which is most likely to be where the shaft penetrates the turbine casing. One of the most commonly used systems for keeping steam and air leakage to a minimum is the gland seal system. We'll be looking at this turbine support system closely in this section. First, we'll take a look at the important parts of a gland seal system. Then we'll see how the parts work together to seal the turbine. This is a close-up illustration of one point where the shaft penetrates the casing. This is the shaft, the casing, the inside of the turbine, and the outside of the turbine. Steam is either supplied or exhausted through these lines. The heart of this system is the gland. The gland is made up of grooves and ridges that form a labyrinth, located where the shaft penetrates the casing. A labyrinth is a maze or tortuous path from which escape is difficult. As this diagram indicates, the grooves and ridges correspond to another set of grooves and ridges on the turbine shaft. The labyrinth seal creates a tortuous path that makes it difficult for steam to leak out or air to leak in. The clearances between these ridges may be as little as 15 to 20 thousandths of an inch. There are usually several glands at each point where the shaft penetrates the casing. However, the glands by themselves aren't enough to do the job. To seal the turbine, steam has to be supplied to these glands. Steam is supplied under pressure to the first two glands, which keeps air out. Any excess steam is drawn off between the second and third glands before it can leak out of the turbine. We'll see how this is done a bit later. In general, the gland seal system functions in one way to seal steam in the turbine and in another to seal air out. Keep in mind, however, that it does both at the same time. To understand how steam and air leaks occur and to see how the gland seal system prevents these leaks, let's turn our attention to the rest of the gland seal system and learn how it functions during the different phases of turbine operation. This illustration shows the major components of a gland seal system. There's a steam supply control valve, a steam unloading control valve, a gland seal supply header, glands, a gland seal exhaust header, a gland steam condenser, and finally, a gland steam exhauster. During startup, before steam is admitted to the turbine is below atmospheric pressure. During this phase of operation, air will try to leak into all three sections of the turbine: the high pressure section, the intermediate pressure section, and the low pressure section. To prevent this, Steam is generally supplied from the main steam line, through the steam supply control valve, to the gland seal supply header. A pressure controller operates this valve to maintain a pressure of approximately 3 to 5 psi in the header at all times. Steam from the header is supplied to the first two glands. Since this steam is at greater than atmospheric pressure, it keeps air out of the turbine. A portion of this steam, and any air leaking past the third gland, is drawn off between the second and third glands. Steam and air from the glands are routed to the gland seal exhaust header. From the gland seal exhaust header, the steam and air travel to the gland steam condenser. Here, the steam is condensed into water, which goes to the main condenser, and the air is removed from the system and vented to the atmosphere by the gland steam exhausters. As steam pressure inside the turbine increases, steam starts to flow out of the high pressure and intermediate pressure sections into the seals. The steam flows past the first gland. A small portion of this steam travels through the second gland and into the gland seal exhauster header. However, the majority of the steam flows into the gland seal supply header. Steam flow into the supply header from the HP and IP sections eventually provides enough steam to maintain the pressure in the header at 3 to 5 psi without an external source of steam. At this point, the HP and IP sections are supplying the low-pressure seals, and the turbine is said to be self-sealing. The system is no longer dependent on an external source of steam, so the steam supply control valve closes. As steam pressure inside the turbine continues to increase, more steam is fed to the supply header, increasing the header pressure. To maintain the header pressure at 3 to 5 psi, the steam unloading control valve opens and routes the excess steam to a low-pressure area, such as the main condenser or a low-pressure heater. Maintaining header pressure at 3 to 5 psi keeps the turbine sealed. Although the gland seal system we've just seen is probably the most common method of turbine sealing, you should be aware that alternative methods exist. One alternative is a water seal. This method involves the pumping of water through a special gland to minimize leakage. Let's look at an illustration to see how a water seal works. The parts of this system include glands, an impeller on the turbine shaft, a water supply line and valve, shrouds, and drains. The supply valve regulates the flow of water to the impeller while maintaining the proper water pressure. The impeller pumps the water into the glands and fills the opening between the turbine shaft and casing. The water in the glands keeps air and steam leakage to a minimum. However, proper sealing cannot be achieved unless the shaft and its impeller are rotating above 1800 RPM. Shrouds around the turbine collect the water and drain it off, reducing water leakage into the turbine. We've now seen why it's important to keep steam in the turbine and keep air out. We've also taken a look at two systems commonly used to seal the turbine. We'll stop here so you can review this part in your text and answer the questions. If you have any problems with sealing systems, ask your instructor for help. We've seen that a turbine has to be properly sealed to minimize air and steam leakage. It also has to be properly lubricated. Otherwise, the rotating parts in a turbine can wear down from friction. The turbine support system designed to lubricate the rotating parts is the lubricating oil system, or lube oil system. One of the most important uses of oil in a turbine is for bearing lubrication. Bearing lubrication supports the turbine rotor, allowing it to rotate while preventing metal-to-metal contact between the stationary and moving parts. In addition, the lubricating oil carries away heat built up in the bearings. Lube oil is also used for hydraulic control systems in some turbines. Since lubrication of a turbine is so important, we need to see how the lubricating oil is supplied to the areas where it does its job. So let's take a look at a typical lube oil system. This is an illustration of a typical lube oil system. Keep in mind, though, that lubrication systems differ in design. The one shown here may not be exactly like the one you have in your plant. However, the principles of operation are similar enough to your own plant's system to give you a better understanding of how your lube oil system works. The basic components of this system are a reservoir, a main oil pump, a booster oil pump, a booster oil turbine, and a pair of oil coolers. To see how these components work together, let's consider each of them as part of a cycle. Let's start the cycle at the reservoir, which is the central collecting point for all the oil in the system. The oil is drawn from the reservoir by the suction of the booster oil pump. The oil is pumped from the booster oil pump to the main oil pump. In this system, the main oil pump is attached to and driven by the turbine shaft. In some cases, oil from the main oil pump is routed to the turbine to be used as hydraulic oil. Hydraulic oil is used to operate the valves controlling the flow of steam through the turbine. Some of the oil leaving the main oil pump is routed to the booster oil turbine and drives it. And the booster oil turbine drives the booster oil pump through a shaft. However, a portion of the oil that leaves the main oil pump bypasses the booster oil turbine. This oil and oil from the booster oil turbine is sent to the turbine oil coolers. The oil coolers are heat exchangers that use water flowing through tubes to cool the oil. The coolers are usually arranged in pairs, with one used for cooling and the other remaining ready as a backup. The cooled oil is routed from the oil coolers to the turbine bearings and other components requiring lubricating oil. Finally, the oil leaves the bearings and flows back to the reservoir, where the cycle starts all over again. The two pumps we've looked at so far, the main oil pump and booster oil pump, are designed to work during normal turbine operation. Since the turbine drives the main oil pump, the discharge pressure of the pump won't be sufficient until the turbine is up to speed. However, during startups and shutdowns, when the turbine is not up to speed, the discharge pressure is not sufficient for adequate lubrication. Therefore, a lubrication system must be equipped with independently powered oil pumps to supply oil until the main and booster oil pumps take over. There are usually 3 pumps on a turbine responsible for supplying oil during startup, shutdown, or emergency conditions. They are the auxiliary oil pump, the AC turning gear oil pump, and the DC or emergency turning gear oil pump. All 3 of these pumps are driven by electrically powered motors. The primary purpose of the auxiliary oil pump is to supply hydraulic and lubricating oil during startup and shutdown when turbine speed is too slow for the main oil pump to be effective. The auxiliary oil pump can also be used to provide hydraulic and lubricating oil during emergencies, such as a turbine trip or failure of the main or booster oil pumps. The next pump, the AC turning gear oil pump, is a backup to the auxiliary pump. If the auxiliary pump fails to start, the AC pump will start automatically to provide lubrication to the turbine's bearings. The third pump, the DC emergency oil pump, is powered by the station battery and is designed to supply lubricating oil when AC power is not available. The DC emergency pump is not intended to circulate oil during continuous operation, but supplies only enough oil to allow the turbine to coast down without damage if all AC power is lost. The DC pump starts automatically if either AC power is lost or if the AC turning gear oil pump fails to start. Up to this point, we've learned how a turbine's lubrication system circulates oil under a variety of conditions, from normal to emergency. However, the lube oil system has other important functions besides the circulation of oil. One of these functions is the removal of potentially dangerous vapors from the turbine's oil reservoir. The component of the lubrication system that's responsible for this is the vapor extractor. A vapor extractor is a small fan connected to the top of the lube oil reservoir. Oil vapor and other combustible gases tend to accumulate in the reservoir and could ignite or explode. The vapor extractor draws these gases out of the reservoir and vents them to the atmosphere. In addition to circulating the oil, the lube oil system is also designed to keep the oil clean. As oil circulates through a turbine's lube oil system, it may become contaminated with dirt, water, and other debris that could damage the turbine. These contaminants must be removed. Oil purification can be accomplished in a variety of ways. One way is to pass the oil through a filter. Inside the filter are skimmers, screens, and a filter medium that removes the impurities. The oil can also be spun in a centrifuge, where the impurities can be separated from the oil by centrifugal force. This particular centrifuge is portable. It can be used for a variety of lubricating systems. No matter how the oil is purified, by filter or centrifuge, the purification process can be done continuously during normal turbine operation, or periodically during turbine shutdowns. Well, you now have a basic idea of how a typical lube oil system works and why it's such an important support system. If you have any questions about the turbine's oil system, reading over the material in the text should help to clear them up. And be sure to ask your instructor for help if you need it. When we return, we'll take a look at two more important turbine support systems. Up to this point, we've looked at the turbine support systems used for sealing and lubricating the turbine. In this part of the program, we're going to look at two support systems used to reduce stress on turbine parts. These systems are the turning gear and the exhaust hood cooling system. The primary function of the turning gear is to keep the rotor turning during shutdowns and prior to startups. It does this for a variety of reasons. To start off, let's see why you have to keep the rotor turning during shutdowns. When a turbine is shut down, hot vapor rises to the upper part of the turbine casing. This means that the upper half of the turbine is at a higher temperature than the lower half. If the rotor is kept stationary, the cooler lower half of the rotor would contract quicker than the hotter upper half. This uneven contraction causes the rotor to bend or bow. To keep the rotor from bowing, it's rotated continuously. Since the turning gear keeps the rotor turning, it's not given a chance to cool down faster on one side than the other. The turning gear consists of a motor that turns the rotor through gears. The rotor turns at a relatively slow speed, about 3 to 5 RPM. The turning gear motor is started and the gears are engaged when the turbine coasts down to a standstill. This motor can be started manually by the operator, or in some cases, automatically by a speed sensor. Normally, the rotor is kept turning even when the turbine is completely cooled and no longer in operation. This is done to keep the rotor from sagging due to its own weight. Although we've seen how a turning gear can prevent a rotor from sagging or bowing by turning it, there are times when the rotor has to be stopped. One example would be when the turbine is taken out of service for maintenance. Whenever the rotor is at a standstill, it can either bow from uneven cooling or sag because of its weight. When the turbine is put on turning gear, the amount of bowing or sagging can be indicated on a recorder, and its numerical value is referred to as eccentricity. Eccentricity is the degree of deviation from absolute roundness, or to put it in simpler terms, it's the amount that the rotor wobbles when it rotates. To straighten out the wobble or eccentricity of the rotor, the turning gear should be operated several hours before steam is admitted to the turbine. In addition to minimizing and correcting eccentricity, another advantage of the turning gear is that it provides for a more uniform and controlled startup. The reason for this is that while it's on turning gear, the rotor is able to generate some momentum before the steam is admitted to the turbine. If steam is admitted with the rotor at a dead standstill, the amount of force required to get the turbine rolling could put a lot of stress on the turbine. In fact, steam normally isn't admitted to the turbine unless it's on turning gear. Now, earlier, we told you about two support systems that help to reduce stress on turbine parts: the turning gear and the exhaust hood cooling system. Let's turn our attention now to the exhaust hood cooling system. The exhaust hood cooling system prevents excessive expansion of turbine parts due to high temperatures. This system is essential during startup, shutdown, and low-load operation, when the steam temperature in the low-pressure turbine is abnormally high. The high temperature in the low-pressure turbine leads to a high temperature of the outer casing of this section. This outer casing is called the exhaust hood. The exhaust hood is bigger than the casings on the other turbine sections, so it expands more when heated. On most turbines, if the exhaust hood temperature were allowed to reach 200 to 250 degrees Fahrenheit, it would expand enough for contact to be made between the rotating and stationary elements of the low-pressure turbine. To control the temperature of the exhaust hood, a water spray system is provided in each low-pressure turbine. This system consists of nozzles installed downstream of the last stage blades. The nozzles spray water into the exhaust hood, which cools it. A control valve controls the flow of water to the nozzles, and this valve is operated to maintain the exhaust hood temperature at about 125 degrees Fahrenheit. The exhaust hood cooling system and turning gear are vital to the turbine's operation, just like the other systems we've seen in this unit. At this point, you've had a chance to learn about several important valves and support systems on a turbine. However, as we've been emphasizing throughout this unit, the parts and systems shown here may not be exactly like the ones you have in your plant. So this may be a good time to stop the tape and have a look at the valves and support systems you'll be working with every day. But before you head out to the plant, read over the material on the turning gear and exhaust hood cooling system in your text. If you have any questions about any of the information we've covered in this unit, or more importantly, if you have questions about any of the valves or support systems on the turbine in your plant, don't hesitate to ask your instructor.